So my name is John Bent. I'm a senior director at Seagate. I work on the Cortex project. I'm an architect on the Cortex project. I also have responsibility and work in advanced development in Cortex, as well as our Cortex open source community. So I'm really excited to give this talk. As is usual these days, it's all virtual, but please don't hesitate to ask questions. And I'll either see them in the chat or Rachel will, or she'll bring them to my attention. So just a real simple motivation for what's going on here and what we're talking about. You've got hard drives and you've got precious things that you want to store on your hard drives. And it seems like it's, very simple, right? You just take your precious things, you put them on your hard drive, and everything is great, right? You've achieved happiness forever. And unfortunately, you think everything is great, but unbeknownst to you, you've got some failures probably in your future, right? And here's some really good failures about, here's some really good papers, some of my favorite papers about storage failures. So if you're interested to learn about all of the things that can go wrong in storage, here's a couple of really good papers. Also, Backblaze has done a lot of good work in this area. Now, if you're not interested in reading all about storage failures, that's also fine. You don't have to be interested in it. I think you can have confidence that, there's a lot of people that are working at this, and there are ways to, protect data from the failures of the storage media. I'll point out that this is not just a modern problem. This is a funny little clip from a favorite movie of mine, History of the World. In Christian religion, there's a story that this guy here, Moses, climbed up a mountain and God gave him the 10 commandments, right? So those are, super valuable pieces of information. And in this movie, they made a joke that actually God gave him 15 commandments originally. But, Moses and God had not thought to protect this very, very important data from the inevitable failure of the storage media. So, what should have been 15 commandments ended up being 10. And in fact, right, as long as the world has stored data, the world has needed mechanisms, right, to protect that data from the inevitable failure of the storage media. So, just a couple of examples, right? People have maybe heard monks in the old days before the printing press. This is how we made copies of books. Monks would just sit there and laboriously copy line by line. On the left is something called a polygraph. This is a cool little tool from the old days that had multiple pens. And, the human would write a letter using one pen, and the machine would simultaneously replicate that letter. Okay. So this is really not a modern, problem. And so replication, as we just saw, has been around for a really, really long time. And replication is also a technique that we use in the storage industry, to protect our data from the inevitable failure of the storage media. And, our disk drives are really, really good. We like to believe, I think it's pretty accurate, they're the best storage media devices in the world. But if you have enough of them, things fail. And that's okay, right? Failure is part of life, but being resilient to the failures, protecting the data from those failures is what's really crucial. And so this technique of replication has been around for a long time, but it's got a high capacity overhead, right? So if you want that picture to survive failures of the devices, you have to replicate it. And if you have, 5-way replication, as is shown, you're using 5 times as much space as you'd like to. So that's a very high capacity penalty. So we can do better. RAID, the redundant arrays of inexpensive disks. This is a work from 1988 by Dave Patterson and Garth Gibson. And so this is just a modern technique to gain durability without that high capacity overhead. It's pretty straightforward. You just take your object, you split it up into pieces, you store a piece on each of these individual drives, and then you create a piece of parity that's the same size as those other pieces. And that parity will allow you to reconstruct lost data. and I'll show you how. I'll simplify it a little bit. Let's just think about it from the perspective of a single bit, right? So imagine that those 4 drives are each storing 1 data bit. So that's the D, right? So the first drive, it has a data bit of 0. The second drive has a data bit of 1. The third drive also 1. The fourth drive also 1. And so now what we do is onto the parity drive, we store a piece of parity data. And it's just, simple logical XOR, exclusive OR operation. And one way to think about it is you just count the number of ones. And if the number of ones is an odd number, then your parity is a 1. If the number of ones is an even number, then your parity is a 0. So it's very straightforward. It's very simple. And now if you were to lose one of those chunks of data, right, maybe because the drive failed or there was some other failure that caused you to lose that chunk of data, it's no problem. You can use that parity chunk to surmise what the initial value of that data was. So in this case, you would say, well, the parity is telling me that before the failure, there were an odd number of ones. I'm looking at the surviving chunks. There's only an even number of ones. That means that the lost data chunk must be a 1. Okay. So just a little bit of terminology that's useful when we're talking about data durability. A chunk is the contiguous piece of data stored to a single device. So in the example of the picture, we split that picture up into 4 chunks, and each of those chunks we store to a device. The chunk size, that's the size in bytes of the chunk or the size in megabytes or whatever. The data chunk, that's one of the pieces of the original data. The parity chunk is the computed chunk that we create to protect the data chunks. The stripe is the name for the collection of all of those chunks that form, a contiguous logical unit of data. The layout is the particular devices on which a stripe is stored. The pattern is a shared configuration of all stripes. So you might have a storage system and you might say, okay, for this storage system, I want my pattern to be 8+2 or 3-way replication, whatever. And then that will be true of all of the stripes that you store using that pattern. Some stripes may have different layouts, however. Full stripe right is something that I'm not going to discuss here, but it's a super important concept for performance. A partial stripe write is a write that's smaller than a full stripe write. Read modify write is the performance inhibition which is caused by partial stripe write. Again, I'm not really going to talk about those here today, but for people that are interested in understanding RAID and erasure, those are important concepts. Pool, we're going to not talk about pool for a while yet. Pool is when we get to declustering, pool is an important concept. And a pool is all the devices on which a stripe could be stored, or all the devices from which a layout could be chosen, would be another way to say that. So next thing I want to think about is how long does it take to rebuild, right? So now we've used this RAID 5, say, to protect our data. And now we have to deal with the failure of one of the devices in that RAID 5 set. So what do we do, right? So how long does rebuild take? Well, the first thing you have to do is find a replacement drive, and we're not going to consider that. A lot of systems have what they call a hot spare or a cold spare sitting in the system that's available. And really what I want to think about is once that replacement drive is available, how long does it take? And what we do is we say, for each chunk that was on that failed drive, you have to restore it. So for each chunk, you read the other chunks from that chunk's stripe from the sibling drives in the stripe layout, right? So you read all of the other chunks that were part of a stripe with the lost chunk. You use the parity to reconstruct that lost chunk, and you write that lost chunk to the replacement drive. Unit here is just synonymous with chunk. So essentially what you have is that the time to rebuild is approximately equal to the time to write an entire drive. Right? We also have all of the reading time involved, but because the reading and the writing are happening at the same time, and because read and write speeds are approximately equal, it's a very good approximation of rebuild time to just say that the rebuild time in RAID 5 is the time to write an entire drive. And how long does it take to write an entire drive? Well, that's pretty straightforward. You know, that's the old distance equals rate times time. The time to write an entire drive is merely the capacity of the drive divided by the bandwidth of the drive. So for example, you know, if a drive was a terabyte big and our bandwidth was 100 megabytes per second, it would take 10,000 seconds to rebuild that drive. So, you know, if we think about the evolution of data durability in data centers, you know, we start with replication and we get RAID 5. And as we go through this talk, I'm going to continue populating this graph and adding more and more of these bubbles. I want to make an important note, which is that this graph here that I'm going to show it's not 100% precise. You know, there's some things that are not quite right. Those dates are approximate. But I think it's a pretty fair facsimile of the general idea of what's happening in data centers and the evolution of data durability. So great, so we have RAID 5, and so the next question is, right, what comes next and what's wrong with RAID 5? So there's a super important characteristic of disks. And this characteristic of disks is that the growth in bandwidth, right? So in 2000 and 2001 and 2002 and year after year after year, the hard drive companies, including Seagate, make new hard drives. And each hard drive that we make has a higher bandwidth than the previous hard drives. And each hard drive that we make has a higher capacity than the previous generation of hard drives. And then, you know, again, that's not 100% true, but that's generally true. And what's also generally true is that the growth in bandwidth is approximately the square root of the growth in capacity. Or another way to say that is that the growth in capacity is approximately the growth in bandwidth squared. And what this means is that drives grow in capacity much more quickly than drives grow in bandwidth. So we're going to talk about that, why that is. So the first question that we need to understand, right, is how do you increase the capacity of your disk? And so in the upper left, one way that you can do it is you can increase the form factor. So that's just the picture of what a disk looks like. You know, and a disk is, I don't actually remember. I should know. It's, you know, it's about 5 inches by 8 inches or something. You could make that bigger. That'd be one way to increase disk capacity. In the upper right, you could also consider inserting more platters. So if you look inside that picture on the upper left, what you have inside is a bunch of these circles. You know, we call them platters. And the platter has an upper surface and a lower surface. In this picture, it looks like we've got about 8 platters, so there's about 16 surfaces. And each of those surfaces is a place into which we store and access data. And so you could imagine trying to put more platters into the disk. That'd be another way to increase disk capacity. On those surfaces, we have a series of concentric circles. Each of those circles is called a track. Each of those tracks has a lot of bits on it, and that's how we store data. We store data into the bits on each track on each surface. For those of you that remember old-fashioned record players, you know, this is a surface is very similar and a platter is very similar to those disks. They have tracks, and those tracks store information. So in the bottom left, a third way that we could increase disk capacity is to put more tracks per surface. And in the bottom right, another way that we could increase the disk capacity, the final way that we can increase the disk capacity is to have more bits per track. Some of you may have heard of a disk technology called shingled drives. Shingled drives is a very cool innovation to increase the capacity of disks. I didn't think to put a citation in here. Another one of my really favorite papers is a paper called Spotlight by Peter Desniers and some of his students from Northwestern University. That's a paper, really good paper that explains shingled drives. And shingle drives is a really aggressive way of doing more tracks per surface. Just a little side note there. So 4 basic ways that you can increase the capacity of a disk. Well, how would you increase the bandwidth of a disk? And there's 3 basic ways to increase the bandwidth of a disk. You could spin it faster. And you can see the picture in the upper left, a little bit of foreshadowing for the talk. Spinning it faster, as you can see from the picture, can be dangerous. You could access more tracks simultaneously. In the bottom left is a way, or you could put more bits per track. And you'll note that that mechanism to increase disk bandwidth, more bits per track, is also a mechanism that we can increase disk capacity. And the reason that increases disk bandwidth is because as the disk spins, the head which accesses the track stays in one place and the disk passes under the head. And if you have more bits per track and you have a constant spin rate, then what that means is that in each rotation of the disk, which is a fixed amount of time because you have a fixed spin rate, you're accessing more data. So more bits per track gets you more bandwidth. So if we look at this, right, and go back to the statement that the growth in bandwidth is approximately equal to the square root of the growth in capacity, and we say we've got these 4 factors for increasing capacity, and we've got these 3 factors for increasing bandwidth, then how do I support that equation at the top? Well, it's because, historically, we don't increase the form factor very frequently. That's a really big thing to do. You're changing all the data centers everywhere that have expectations about drive size. Inserting more platters, happens very, very infrequently. That's hard to do. So generally, when you get, a next generation disk, the reason it has more capacity is those bottom 2 factors. And in terms of increasing bandwidth, it's disk people talk about revolutions per minute, disk RPMs. Disk RPMs have been, mostly flat if you look at that over the years. Accessing more tracks simultaneously, that also does not happen very frequently. But more bits per track does. So you see that, we generation after generation, there's 2 main factors increasing capacity, 1 main factor increasing bandwidth. Now, let me just make a little caveat. There is a new technology from Seagate that we're very proud about called Mach 2, which is a technique to access more tracks simultaneously. But disregarding that, it does happen, but it doesn't happen in every generation of drive. So typically, and what's been true over the years, is that it's those 2 factors and that 1 factor. Those 2 factors for capacity, that 1 factor for bandwidth. And so what this means is that the bandwidth of disk n+1, and n+1 to mean, the next generation, right? So the next generation bandwidth of the bandwidth of a next generation disk is effectively the bandwidth of the previous generation disk times the growth in bits per track. And the capacity of the next generation disk is approximately the capacity of the current generation disk times the growth in bits per track times the growth in tracks per surface. Something else is that, I'm just going to tell you that the growth in tracks per surface is approximately equal to the growth in bits per track. Now, again, shingle drives was a bit of an outlier there, but generally that's a true statement. So what that means is that the capacity of the next generation disk is approximately equal to the capacity of the current generation disk times the growth in bits per track squared, and that leads us to the growth in bandwidth is approximately equal to the growth in capacity. All right. So now, what does that mean? Well, if we remember that the time to write an entire drive equals the capacity of the drive divided by the bandwidth of the drive, and we also take into consideration that, this very key consideration and aspect of disks, that their bandwidth grows more slowly than their capacity. What that means is that essentially the probability of data loss using RAID 5 approaches 1. So just a couple of graphs to show this. So the graph in the upper left, and I put the reference where these graphs came from. It's a nice blog article. The time to rebuild your drives as your drive size goes up, and your drive size goes up with each new generation of drives. So the horizontal axis in that upper left graph shows the drive size in terabytes, but it can also show, the year, essentially. So the time to rebuild goes up and up and up. And in the bottom right, we see the statistical probability of failure, right? So if it takes a really long time to rebuild your drive during failure, that's dangerous because you're in a vulnerable window. If you encounter another failure before you finish your rebuild, then you will have lost data irretrievably. So your rebuild has to be fast enough that it can complete without a probability of subsequent errors. So the bottom right graph is showing that as your drives get bigger, you're approaching, 100% probability of losing data during the rebuild. That's the blue line showing RAID 5. There's also an orange line which shows the probability of failure for RAID 6. We haven't talked about RAID 6 yet, so that's another spoiler alert. You can ignore that for now. So what comes after RAID 5? RAID 6. Right, so we've got the same picture, we split it up into chunks, we added a parity chunk, but now what we've learned is that the rebuild time is really dangerous, so RAID 5 is not good enough. What do? We introduce RAID 6, which we introduce another drive. Onto this drive, we store another chunk of parity that's different from the first chunk of parity. All right, and how does RAID 6 work? Well, the way I think about it is using high school algebra. RAID 6 is really just two equations and two unknowns. So imagine that instead of just storing an individual byte, that each of your pieces of data is an integer, for example. Then what your first parity chunk will be is the sum of those integers. And your second parity chunk will be the product of those integers. And by the way, I have to admit, I've been doing distributed systems and distributed storage for a long time now. And I think that I understand things okay at the systems level. I don't understand the math. I'm not a mathematician. So, this is probably not accurate. I noticed that there is a mathematician on the call. He's probably, rolling around on the floor right now in agony at how inaccurate this is. I apologize to him. But from a systems perspective, this is how it works. And this really gives you, I think, the information that you need to understand. And by the way, also, this exact thing, another reason this exact thing wouldn't work is because of things like integer overflow when you store variables. So I don't understand the math, but this is approximately the math. And now what happens if you imagine you've lost two of those data chunks, either because the drives failed or some other failure caused you to lose those data chunks. Now you've got your two equations and your two unknowns. Your missing data chunks are, referenced as variables x and y. You do some math, you're able to restore your data chunks. So what comes after RAID 5? RAID 6. Great. Well, what comes next and what's wrong with RAID 6? So it turns out that this same exact thing that was wrong with RAID 5 is wrong with RAID 6. And we saw that in the earlier graph, right? That disks continue to grow more quickly in capacity than they do in bandwidth. And therefore RAID 6, which was good enough for a while, is no longer good enough. Okay, RAID 5 was good enough until it wasn't. RAID 6 then replaced it. RAID 6 was good enough until it wasn't. So finally, we're going to move on to talking about what declustered parity is, except we're not quite there yet. So when we talk about declustered parity, we have to imagine that we've got lots and lots of drives. If you have a small number of drives, declustered parity is not an option. So here we've got 100 drives. And one of the ways that the industry would protect data when they had 100 drives in the past was with fixed groups doing either RAID 5 or RAID 6. So here you see that we have 100 disks, and we split them into 10 fixed groups, and we've got 2 of these spares. And so now every time that we want to store data, we choose one of those RAID groups and we store data into that RAID group. And what happens when you have a failure is this is that same problem that we've been talking about. For every chunk of data that was on the lost drive, you have to read the corresponding chunks from its stripe from the sibling drives, and then you have to restore that missing chunk to one of those spare drives. So you see, again, how long does the rebuild take? It takes the time to write an entire disk. The time to write an entire disk is going up, up, up with each generation of disk. This is the problem. So what is declustering? Well, declustering takes those same 100 drives, but instead of having 10 RAID groups, declustering will say, we're just going to have one giant pool, one declustered group. And we can still have those same 2 physical spares. But what you see with each of those 100 drives is you see a little gray rectangle at the bottom that's probably too small to see. There's some letters on there that spell out virtual spare. So that's the first really key critical concept in declustered parity, which is that you have a virtual spare. So from every single drive, we are going to create a partition and we are not going to store any data on that partition. And that's called the virtual spare. And as when we talk about erasure especially, we talk about n plus k. So n is the number of data chunks, k is the number of parity chunks. And in declustered parity, we also introduce this concept of S. And S is spare drives. So with n plus k plus S, it's how many drives worth of spare space do we reserve? And so now what happens when there's a failure is that what we do is, let me skip replay phase. So we have the concept of virtual spare. The next important concept is actually the third one there, the pseudo-random layout. And pseudo-random layout means that maybe in this case with our 100 drives, we're still going to do a stripe pattern of 8 plus 2. But for every stripe that gets stored into this declustered pool of 100 drives, we will pseudo-randomly choose 10 drives to lay out that stripe. So every stripe goes to a different random n plus k drives. And then rebuild is all to all. So in this case, it would be 99 to 99. So now imagine the case where one of those drives fails. What do? For each chunk of lost data, we figure out its sibling drives. And those sibling drives are a pseudo-random selection of 9 drives out of the 99 surviving drives. And we use those 9 drives to reconstruct the lost chunk. And then the really critical concept is we write that lost chunk to pseudo-randomly selected one of those 99 drives. So what that means is that the rebuild time is the time to write a disk's worth of data across all of the drives. So with our fixed redundancy groups, the rebuild time is the time to write a disk's worth of data to one drive. And that's the whole problem that we've had. And now what we're doing is we're writing a disk's worth of data to all of the drives. So the amount of data that we're writing is fixed, but the time that it takes to write that data scales with the total number of drives, with our pool size. So the larger the pool, the better the rebuild. And then the other concept is the replay phase. So we do the declustered rebuild very, very fast. But then we've started filling our virtual spare space. So what we want to do is we want to then bring another drive in, and we will do a replay of writing the disk's worth of data from the virtual spare into the physical spare. And that can take a long time, but that's fine because we are not on the critical path. The critical thing to do is restore redundancy. Once redundancy is restored, we can take our time to do the rebalance. So if we were to look at, the failure scenario here, there would be not just 9 arrows pointing to one of those physical spares, there would be 9,702 arrows because each of the 99 drives would have 98 arrows to each of the other drives. So I did briefly consider trying to add those arrows. I figured the only way that I could possibly do it was by programming something up. I apologize, I didn't get to do that. But please imagine an overwhelming number of arrows on this picture, and you will see the tremendous scalability power of declustering to improve rebuild. So I did take some time to create just a very simple GNU plot. You can see the entire GNU plot on the right. So there's a very small number of lines. And what this shows is, as a model, and obviously we have the measured data as well to show this empirically. But what you see is that the rebuild time in hours, for a 20 terabyte drive, if you were to do fixed erasure groups, is more than a day. But as you grow the size of your pool, the declustered erasure group can bring your rebuild down to under an hour. And the link is there if anyone wants to play with that, and if anyone does, I'd love to see what you do with it. Okay. So we had RAID 5, we had RAID 6, awesome, great. And then at the enterprise, we moved to declustered RAID 6, which is N+2 plus S. And even N+2 plus S with the declustering, hey, that's still a great technique. But for even better durability, we have some customers out there that prefer larger values than 2, to make their data even more durable. So that's declustered erasure with N+K plus S. Meanwhile, in the public cloud, things like the Google file system, the Hadoop distributed file system, those things started off with 3-way replication. They went back sort of to the replication days. It was declustered, by the way. And then they moved to declustered network erasure. By the way, just, this is really a general talk, but I am part of the Cortex team. I am part of the company at Seagate. So I do want to point out that Cortex Community, the Cortex Object Store that I work on, is an example of declustered network erasure. And Seagate is making some really nice products in declustered RAID 6 and declustered erasure that are called Core Vault. There's lots of good information about both of those things if you're interested. So what comes next? What's wrong with these? All right. So there's really 2 existing approaches for data durability and availability. On the left is hardware local declustered erasure, and that's systems like Lustre, BGFS, PVFS, other systems like that. Those are examples of high performance computing distributed file systems. And what those systems do is at the network level, at the client level, they just take their data and they split it up, and they send their data to these high availability server pairs that run on top of hardware RAID. So that's how those systems get their data durability and availability. Other systems, I apologize for the word drop there. Other systems using software networked declustered erasure, like Cloudian, ActiveScale, so StackSF, HDFS as well, are doing the opposite, where they're not doing hardware RAID, they're doing software RAID. It's not local erasure, it's network erasure. So what they're doing is at the network level, they're adding the parity there, and they're sending it to just single servers running JBODs. And what it turns out is, if you look at another really good paper that I like a lot, that extreme scale requires extreme protection, and neither of those approaches is really sufficient. So what this graph on the right shows is failure events. And a failure event is a failure event where some number of storage nodes failed at approximately the same time. And those storage nodes or those storage devices were distributed across some number of racks. And the size of the circle is how often a failure event of that signature occurred. And the height of the circle on the vertical axis is the number of nodes that were affected. And the position on the horizontal axis is the number of racks across which those nodes were distributed. So that's why there's nothing below the diagonal, right? So if you look at the circle at 2, 2, that means it's a big circle. So that means that there were lots of times that in their study, they observed 2 nodes failing on 2 racks. And, so there can't be something like, there's nothing below the diagonal, because it's not possible that you could have, 2 storage devices fail that were on 3 racks, right? So the diagonal is the limit there. And this data is really interesting. And what you see is that there's sort of 2 types of failure events, right? One is a spatial failure burst. So a whole bunch of storage devices failed at the same time on the same rack. And this is a well-known failure event, and this is why the Google file system and the Hadoop distributed file system spent so much time talking about protecting their replicas by using multiple racks, because it's well known that the rack is a failure domain. So there's lots of failures that happen where an entire rack fails and all the devices on that rack fail. So I think that blue oval there, those failures, is not really a surprising event. What is a surprising event, when I first read this paper and thought about this paper and talked to some of the authors about this paper, is that you also have these aspatial failure bursts, where you have lots of devices that are failing at the same time across different racks. And so, your rack-aware placement will not protect you against those failures. And it's confusing, right? And so some of the reasons why you might have an aspatial failure burst is because, well, it might actually be a spatial failure burst, right? It might be that you had a sprinkler event in your data center. And so you had a bunch of storage devices at the tops of your racks fail. So they're in different racks, but they have a spatial correlation, that they're all near the sprinkler. Or you could have a flood, and then you'd have a spatial relation across lots of racks, in that they're close to the floor and they got affected by the flood. You might also sometimes have these aspatial failure bursts that don't have any spatial relation. And that might be, a bug in the firmware could cause a lot of failures at the same time, a bug in the software. You might also, some of those failure papers that I referenced earlier talk about the bathtub curve of mortality. You might have drives that are at similar places in their bathtub mortality curve. So there are reasons for that, but it is a more surprising, less intuitive type of failure event. And so what we see is that there's no single tier of parity that can protect across all, against all of these. Kudos to Google. They were awesome to publish this study. It's a great study. They never published how to solve it. I assume that they solved it, but they never told anyone how, right? So what Seagate's trying to do is trying to make solutions to that problem available to our enterprise customers using our Cortex system and our Core Vault system. And so if we look at that hardware local declustered erasure, it's got a durability problem. It cannot protect against those aspatial failure bursts. And the software network declustered erasure has a similar problem, but the opposite, which it cannot protect against the spatial failure bursts. There's also some cost issues. There's also some availability concerns. I'm not going to get into that here. So now what we're doing is we are advocating for the use of multi-level erasure coding. So what both of these traditional systems do is just a single layer of erasure coding. What they do is they take some object, they split it up into those green data chunks, and then they add those orange or those yellow parity chunks. With hierarchical or multi-level erasure coding, we first take that object and we split it up into data chunks and one giant parity chunk. And then each of those chunks goes then to local erasure groups, which then further split it into data chunks and parity chunks. So in the far right, all of those green data chunks are actually parity chunks, right? And those are and then those orange squares within the large orange square on the right are the parity of the parities. Now you might think, oh, well, this is introducing more capacity overhead. That's not quite right, and I'm going to get to that in a second. Okay. So what is this approach that we're advocating? We're advocating two levels of erasure. One, we're doing the network erasure. We're also doing the local erasure. And we're also saying, you know, that design with the high availability servers was a good design, and we should bring it back. So now what you see, right, is that there's all these different failure events that we can handle that a single level can't, right? So, you know, a couple of drives, we repair them with local RAID. This is also really good. A lot of people are worried about the rebuild traffic going over the network. So, you know, this is an approach where most of the, not all, most of the rebuild traffic is protected from the network. If we are to have a catastrophic failure event, as is possible, as we saw in that Google paper, no problem. We have the network erasure. If a server goes away temporarily, no problem. We have the high availability server backup. If we lose that hardware RAID unit, again, you know, catastrophic failures happen at very large scale, no problem. We've got the network erasure. Okay. So here is a lot of data from the mathematician who's on the line about the value of multi-level erasure coding. So what the vertical axis here is the durability. You know, so how many nines of data durability do you have? Higher is obviously better. And the horizontal axis is the capacity overhead. All of those orange squares are single level configurations, and the blue square is multi-level configurations. So sort of the basic rule here is you add more overhead to improve durability. So each of those lines of dots, you can see, right, that as you add more capacity overhead, right, like the orange diamonds at the bottom, you can somewhat, you know, minimally increase the durability by increasing the capacity overhead. That's the basic rule. But the advanced rule is use multi-level to improve durability without increasing overhead. And so this green circle that I've got there is 4 different configurations, all of which have the same total amount of capacity overhead, right? They're all about 25%. But by organizing that same amount of capacity overhead into a multi-level configuration, you're getting, you know, multiple nines of additional durability. So what comes next? Well, this basic multi-level erasure, like what I just described. What comes beyond that is some ideas that we have for going even beyond declustered. And there's a longer video where I talk about some of those concepts, and the link is there. With that, that is the material that I prepared today. I thank everyone very much for joining the call. I really appreciate all of the interest in the work that we're doing. We are always super eager to get feedback. I imagine that there's, as I mentioned before, you know, the general idea of this graph I'm comfortable with. I think it's pretty accurate. The precise location of these circles, you know, there's definitely some things that could be argued about there. So I'm really interested in any and all feedback that people have. For example, I think GPFS was a little bit earlier maybe to some of the declustered stuff. Panasis had sort of an interesting declustered grade 5, you know, somewhere in this period. So there's definitely some inaccuracies, and would love to hear what people think. And I believe we have some time if there's any questions now.
I'm just changing the options, so anybody who wants to unmute themselves should now be able to do so if they'd like to ask a question.
Hi, John. I'd like to know, I'm still not very clear about the local hardware decluster erasure coding and the network erasure. You said that the lateral file system is the local hardware erasure. The Hadoop is the Hadoop file system is the network decluster erasure. So can you elaborate the two, the difference between the two, the lateral file system and the Hadoop file system?
Yeah, absolutely. Thank you so much for the question, Arthur. It's a great question. So imagine that you have a megabyte file, or let's imagine you have a gigabyte file, and you want to store that file into Lustre. So you're going to give that gigabyte, and you're going to say, "Hey, Lustre client, take this gigabyte and store it for me." And what that Lustre client will do is let's say it will split it up into 10 100 megabyte pieces of data. You gave it a gigabyte, and it splits it up into 10 100 megabyte units. And then what that Lustre client will do is it will choose 10 Lustre servers. I mean, there's some extra complexity, but generally, right, it will choose 10 Lustre servers. And to each of those Lustre servers, it's going to say, here is 100 megabytes of data. Please store this. Then that Lustre server will just take that 100 megabytes of data and it will write it to its disk. And that's all that Lustre does. Now, I don't know exactly where Lustre is today. There is work in adding redundancy at the Lustre level. I don't know the status of that work. But as of, no more than 2 years ago, for sure, and maybe still today, Lustre is not adding its own redundancy at all at the software layer. So if you went out and you installed your own Lustre system, you could run Lustre with 10 servers and 10 disks, and Lustre would take your 1 gigabyte file and store it like I described. And then if one of those disks fails, you just lost data. So what people do when they install Lustre is they don't install Lustre just on top of disks. People will take Lustre and they will install it on top of hardware RAID. So Lustre relies on the hardware to add data durability. So now each of those Lustre servers, the Lustre server itself doesn't even know. But the Lustre server itself, in almost all installations of Lustre, will write that 100 megabytes of data to a hardware RAID system. And then the hardware RAID system will take that 100 megabytes of data from Lustre, and it will then split it up even further into chunks, and it will add parity chunks and protect the data like that. Mm-hmm. What Hadoop does, on the other hand, is Hadoop will take your 1 gigabyte file, and Hadoop will also break it into 10 100 megabyte chunks. But then what Hadoop will do is Hadoop will add parity at the network level. And Hadoop will then add, say it was 8 plus 2, Hadoop would add 2 parity chunks of, 100 megabytes each. And then Hadoop will find 12 servers, and Hadoop will send those 12 chunks to those 12 servers. So at the end of the day, the capacity overhead is the same. Lustre chose 10 servers and stored 100 megabytes, and then each of those RAID systems that those 100 megabytes was stored to will amplify the data by 20%. So you end up with 20% capacity overhead. Hadoop, it adds the capacity overhead, it adds the parity at the network level before it stores, but then each of those servers, when it gets the data, doesn't add any further redundancy.
Mm-hmm. Okay, so that means Lustre file system, they don't have the network level erasure coding. So they totally rely on the hardware RAID level for the data protection. So that means our storage array, Seagate storage array, will take the responsibility for the data protection. So that means all the disk failure will not reflect in the network bandwidth, right? While in the Hadoop, because they don't use the array, they just use the JBOD. So if any disk failure, that will causing a lot of replication or traffic in the network. So that will cause network storm, network traffic storm, something like that. So is it possible that also we use the ABOT, the rate in Hadoop, that some disk level failure also can be resolved within the array, within the storage array level, and that don't need to causing the network traffic storm. Is it possible?
Yes, Arthur, that's 100% possible, and that is 100% what we are advocating. And Sergey Ohms at Seagate is the mathematician that has proven to us that this is the right thing to do. And really, you're discussing another advantage. So the advantage that you're discussing is keeping the bulk of the rebuild traffic off the network. But even beyond that, using RBOD with Hadoop will increase your durability. So there's two ways to do it. So Arthur, what you could do is if you used RBOD with Hadoop, and for those in the audience that don't know, RBOD, JBOD is what we call just a bunch of disks. RBOD is what we call a reliable bunch of disks. So RBOD is when you have the hardware add the redundancy and the data durability for you. So you can absolutely build, what we think you should do is we think you should build Cortex with RBOD. I have to say that I'm on the Cortex team, but you can also build whatever you want with RBOD. And if you're building Hadoop, you could build Hadoop with JBOD, or you could build Hadoop with RBOD, and you should use RBOD. And now you've got two ways to do it. You could either completely turn off all of the durability at the Hadoop level and just build Hadoop with RBOD, which would make Hadoop look like Lustre. Or you could turn down the redundancy in Hadoop. Let's say that there's a data center out there that says the level of redundancy that I want is 8+4. And so they've been running Hadoop with 8+4. Well, what you should do is instead of setting up your RBOD to do 8+4 and turn off redundancy at the Hadoop level, you should set up your RBOD to be 8+2. You should set up Hadoop to be 10+2. And now your total amount of capacity overhead is equivalent to having 8+4. Basically, what you're giving yourself is you're choosing, instead of one of these orange squares with 25% capacity, you're giving yourself one of these blue dot squares with the 25% capacity.
Yes, the efficiency of the storage will be enhanced. So
100%.
Yeah.
Now, there is a trade-off, and it's when I gave the terminology at the beginning of the talk, I talked about full stripe write, and I said we're not going to talk about that in this talk. And full stripe write is an important consideration for performance. What you get when the trade-off when you go to the blue as opposed to the orange is your full stripe write gets larger. So you just have to more carefully control your workload.
And John, also, can you help me to understand better about the concept in our adapt erasure coding? What's I don't understand very well the concept of the stripe zone. The stripe zone. I still not very clear about the stripe zone. Yeah.
So for those in the audience that aren't familiar, Arthur's question is referring to Core Vault. Core Vault is the RBOD systems that Seagate is selling. Inside Core Vault, we refer to the firmware that runs inside Core Vault as Adapt.
Yeah.
Arthur is asking about stripe zones. So Arthur, when I talked earlier about in declustered erasure, we do a pseudo-random layout. And what that pseudo-random layout means is you've got all your disks in your disk pool, and for each stripe, you pseudo-randomly choose from all of the other stripes. So that means that in theory, the total number of layouts that you could have, say you had like 100 drives and you wanted an 8+2 pattern, then the total number of layouts that you could have would be 100 choose 10. It'd be some very, very large combinatorics. You know, again, I have no idea what that number is. Sergey's on the call. He probably already knows. It's a very large number of possible layouts. And it turns out that to get the benefits of declustering, you don't need to allow every single possible layout. So I believe, you know, and you'd have to ask somebody else who knows Core Vault better than I do, but I believe that what stripe zones are is constraining the total possible number of layouts. And what that allows you to do is it allows you to have simpler algorithms for choosing a layout without sacrificing the durability that you get from the declustering.
Yeah, so I understand that the stripe should be the 8+2, the stripe set, right? 8+2 is the stripe set or layout. It should be randomly right to 10 disks, right?
Correct.
Yeah, so it should not be continuous writing to 10 disks until the stripe zone become ready or full. A stripe zone is said it's is it 4 megabyte or?
I think so. I think in a typical Core Vault configuration of 8+2, they're doing 256K chunks. So maybe your stripe is 2 megabytes. Maybe they're doing 512 chunks.
A 4 megabyte stripe late. Okay, so I feel hard to understand the stripe zone. Because I think every stripe set 8+2 will be distributed or to the randomly to all the disks in the groups, right? That's my understanding. So how come there is a stripe zone? I don't think there should be a zone there. How to define this zone? So I feel that difficult to understand this. Yeah.
Yeah, it's a challenging concept, you know, and we've gone a little bit over. I'll just say that there's considerations when you choose those layouts, because imagine that the user is writing 2 consecutive logical stripes. Your sequential performance is better on hard drives than your random performance. So what you would like to do is you'd like consecutive stripes to go to the same drives so that you can do sequential IO to the same drives. But if you do that too much, then you're not using all of the drives. So there's all sorts of different you know, trade-offs, and the team has spent a lot of time trying to find the proper balance between sequentiality and load balancing.
Okay, thank you. Thank you, John.
Yeah, thank you for your questions. Really appreciate the interest.
So thank you so much for attending. As always, please reach out to us. You know, you can find us on GitHub. Just follow our short link here, cortex.link/GitHub. You can join our newsletter and find out about all of these talks and get, you know, for when you want to review this, see the YouTube video that we'll be putting up. You can check us out at cortex.link/newsletter. Sign up for that. Once a month, you'll hear from us. Or if you want a cool Cortex sticker, cortex.link/stickers. Although I will tell you that we tend to send them out in batches, so it may be a few months, but we do send them. So, all right, thanks so much, and we hope to see you next month.